Hello everyone. Today we will discuss about the energy band diagrams for intrinsic and extrinsic semiconductors. So for intrinsic semiconductors, we know that the number of electrons is equal to number of holes if the temperature is above 0 Kelvin. But at 0 Kelvin, no free electrons are possible and no holes are there. So that's why a semiconductor behaves as an insulator at a temperature of 0 Kelvin. Right? So we are talking about temperature at 0 Kelvin first of all in case of intrinsic semiconductor. So first is intrinsic. So this is at 0 Kelvin. And second case we will discuss for temperature greater than 0 Kelvin. So for the first case, if we talk about the conduction band here, and valence band here, and we know that this is increasing energy. So at 0 Kelvin, only valence band has electrons and no electrons are there in conduction band and no holes are there in the valence band. So we can say no electrons and no holes at 0 Kelvin. So it behaves as an insulator. Now let's discuss the second case when the temperature is greater than 0 Kelvin. So for temperature greater than 0 Kelvin, some electrons may leave the bond and will create a hole in its place, right? That we have already studied in the previous video. So what will happen if we see the energy band diagram? So in case of energy band diagram, here these energy levels, closely spaced energy levels in valence band. This is the conduction band, and some electrons may leave the valence band and form holes at their place and reach the conduction band. So in this case, the electrons have crossed the energy gap and are free in conduction band to conduct. So this energy gap which is less than 3 electron volt in case of semiconductors. For germanium it is 0.72 electron volt. And for silicon, this is nearly equal to 1.1 electron volt. So this lowest energy of conduction band is represented by EC. This is the energy of valence band. So when the electrons in valence band, these get sufficient energy at room temperature to cross the energy gap, then these electrons reach the conduction band, creating holes in place of this. So these are the holes. We can say that here 4 holes are created in place of 4 electrons which gain energy greater than energy gap to reach the conduction band. Right? So there is no impurity in intrinsic semiconductor. So that's why you can say that number density of electrons is equal to number density of holes. Right? So these are important points here. That's why a semiconductor conducts above 0 Kelvin, but at 0 Kelvin it behaves as an insulator. So you can say here above 0 Kelvin. Now we can discuss the extrinsic semiconductors. We know that we have studied 2 types of extrinsic semiconductors. One is p-type and the other is n-type. So first I'll write the heading here, extrinsic So first I am writing here p-type. We know that in p-type semiconductor, which type of impurity is added? Trivalent impurity is added. So we'll just mention it because we need to use that concept here. So if we look at the conduction band, this conduction band is here. Again, the valence band is here. Now we know that trivalent impurity means it is short of 1 electron. So you can say that with every impurity atom, a hole will be created, right? And hole is created, that means deficiency of electron. So you can say that it will be a acceptor impurity. So you can write here trivalent impurity is also called as acceptor impurity because it can accept an electron. Moreover, in p-type semiconductors, number of holes is greater than number of electrons. And number of holes behave as positive charge. So that's why you can relate this P to positive. So P type, number of holes is very greater than number of electrons. So P corresponds to positive, as holes are positive. Right? Now, in valence band, this is the valence band. In valence band, these are closely spaced energy levels. Now here, with every impurity atom, an additional hole is created. So you can say here that suppose 1, 2, 3, 4, 5, 6, 7, 8. I'll draw more lines. How many holes are visible here? 9 holes are there, right? Suppose one electron leaves its place and by gaining energy equal to energy gap, it may reach the conduction band. So in conduction band, this one electron is due to the crossing of this electron, due to the crossing of the energy gap by this electron on gaining sufficient energy. But rest of the holes are due to this acceptor impurity, which is trivalent impurity. So here if you look at this, you can say that each impurity atom creates a hole, right? So in the above figure, 8 holes are due to the impurity atoms and 1 electron hole pair is created due to thermal agitation. So in the above figure, 8 holes are due to 8 acceptor impurity atoms and 1 hole is created by crossing of energy gap by 1 electron. So you can say that 1 electron hole pair is created by thermal agitation. And what is thermal agitation? That when the temperature rises above 0 Kelvin. So you can say temperature greater than 0 Kelvin. So here one more thing is there, that this is an acceptor impurity. So acceptor impurity gives rise to an energy level which is called as acceptor energy level. just above the valence band, right? So what happens is that this energy gap is very less. So this energy gap can be easily crossed by the electrons in the valence band and they reach the acceptor level, creating a hole in its place. So that's why here mainly the conduction is due to the holes. So holes are easily created as the acceptor energy is very close to the valence band. So you can write down here acceptor energy level. So we can just mention these points. EA is very close to valence band. Therefore, electrons easily gain this small energy to reach EA, thus creating a hole in valence band. So that means the holes are the majority carriers in p-type semiconductors. Because number of holes is easily created because this acceptor energy level is very close to the valence band, while in conduction band only a few electrons, like in this case only one electron is there in the conduction band because energy gap is comparatively larger than acceptor level energy. And here we know that the energies are increasing this way. So this was about p-type semiconductor. Now we talk about n-type semiconductor. We know that in n-type we have pentavalent impurity. That means 5 valence electrons. Here we know there were 3 valence electrons. Now what happens in this case? Again here this is the conduction band. This is the valence band. We know that this is pentavalent impurity. That means each impurity atom is giving an extra electron. So we can write, just a reminder though we have studied this, This is also called as donor impurity, as it gives an extra electron, since each impurity atom gives an extra electron, right? So that's why this is called as donor impurity. Now, therefore, in n-type, number of electrons is very greater than number of holes, or you can say number density of electrons is very greater than number density of holes, right? And we know that n corresponds to negative. So you can remember this as well. N corresponds to negative, as electrons are negative. So you can remember that n-type semiconductor, we have extra electrons due to the donor impurity over here. Now, we have already studied in the previous video that this fifth electron is extra. So the 4 electrons which are covalently bonded to the 4 silicon atoms, or you can say the 4 pure semiconductor atoms, these are seen as core electrons. So this way the fifth one is loosely bound and it can be freed easily. So this easily attains a level which is very close to the conduction band. So this is called as donor energy level, and this is denoted by ED. This energy gap is very small. So each impurity atom is giving an extra electron which is easily reaching the conduction band due to this very small energy difference. Now here I can draw this 1, 2, 3, 6. You can see here that there are 9 electrons in the conduction band. If I draw 10 electrons, fine. These are 10 electrons in the conduction band. So out of these 10 electrons, 1 electron hole pair is created by thermal agitation, but 9 electrons are due to the donor impurity. So you can mention over here that in the above figure, 9 electrons are given by 9 impurity atoms and 1 electron hole pair is created by thermal agitation. And we know that the energy required to free this fifth electron is very small. So that's why the donor energy level, or you can say the energy required to cross this very small gap, is very small, since fifth electron is loosely bound to the donor atom. So that's why it gets more number of electrons in the conduction band very easily due to the donor atoms. So we will just mention it, donor energy level lies just below the conduction band. So the loosely bound extra, or you can say fifth electron, easily crosses this energy and reaches conduction band, right? So this is the valence band, and we know the meaning of all these terms, conduction band and valence band. If you want me to write that again, that here CB is conduction band, VB is valence band, EG is energy gap. So this was all about this energy band diagram. We can mention one more thing over here, that in this case the electrons are the majority carriers. So you can remember this easily. N type means electrons are majority carriers. So this was all about the energy band diagram for the intrinsic and extrinsic semiconductors. That's all for now. Have a nice day.